All right. Well, hey, welcome to week 2 of differential equations. Yep, already there, week 2. Not that I'm counting, but I'm counting. I know you guys are too. At this point, you guys all know where you're going. You got your transfer stuff all set up. You're just counting the clock or watching the clock, and you just know that you got to pass this class and everything's good. Um, well, today's plan, we're going to actually talk a little bit about the theory behind solving these first order differential equations. Like, when do we know we've got solutions and that. So we're going to talk a little bit of theory, but before we get into that, I know you guys have some homework due tonight. So is there anything you guys want to talk about from the first few sections, or you have any questions about the methods that we've created to solve anything?
The method on the couple of last questions of 2.1,
Okay.
that one I know how to do it, but I'm not sure if I understand it.
Okay. We'll go take a look at that. Anything else? All right. Well, as always, if anything comes to mind, go ahead and throw it in the chat box and we can look at it. But let me start by sharing my screen here and we'll go take a look at section 2.1. Do you remember what the problem numbers were, Victor?
48, I think.
So the solved by the methods discussed in 47.
Yeah.
Okay. All right. So let's just take a look at 47 first. And so it says here that some nonlinear equations can be transformed into linear equations by changing the dependent variable. Okay. So it says, show that if we've got this form, g prime of y times y prime plus p of x times g of y equals f of x, where y is a function of x and g is a function of y, then the new dependent variable z equals g of y satisfies the linear equation. All right, so this is another trick that's really, really common when it comes to differential equations. The first trick that I showed you that we talked quite a bit about last time was the integrating factor, right? Where you multiply by, you go, all right, I know a solution to the homogeneous, but I need non-homogeneous. So how about I just multiply by u or whatever, right? So there's always that trick, just multiply by something. Another big one is to replace. It's like u substitution. The idea here is you're doing like a u sub, and it works. That one works a lot for very specific forms, and that's what they're getting at with this guy. We've got a really specific form here that we want to show will allow us to do this substitution. All right, well, let me first show you, and well, I'll just go ahead and draw it on here because I can draw on the PDF. Blue works for me. Let me show you why this is going to satisfy this differential equation. So let's actually plug it into here. So we're going to take this z, trying to draw, don't. Oh, are you kidding me? This one's not going to let me draw on it? All right, well, then let me go to a whiteboard. Okay, so the linear that we are looking for was z prime plus p of x times z equals f of x, right? And we are told that z is equal to g of y. So let's just actually plug this into the differential equation and see what it does. So z prime is going to be g prime of y times y prime. Why is it g prime of y times y prime?
because g of y is a function of y, and so you got to differentiate y still.
Yeah, so it's chain rule, right? I mean, it's chain rule, implicit differentiation, however you want to think about it. But that's exactly right, Bradley. It's chain rule. So that y still has to be differentiated. All right, so let's put these into the respective places. Sorry, my windows are all getting in my way here. All right, so we're going to put the g of y in there. So that gives us g prime of y times y prime plus p of x times g of y equals f of x. So if we just went with this substitution, plug it into this linear guy, it turns it into this form. All right, well, let's go back and look at the book real quick. Right, so we see that was the differential equation we just plugged into. And what it ended up giving us was exactly this form. So if we have this form, we can make it linear by just letting z equal g of y. But notice that this is a very specific form, right? It's a very specific form that we've got some function being multiplied to p of x, but then its derivative times the y prime. So really, to recognize that you can use this substitution, what I do is I look at the piece on the y prime and I think about, is its integral being multiplied to the p of x? So come back here down to like 48a. So you notice here we've got secant squared y times y prime. Well, secant squared's integral is tangent. So it's got the right form. This one, the y bit, it's 1 over y. 1 over y's integral, natural log of y. Right, so that's how you can recognize if this form is even applicable. And if it is, you can just do this substitution and then be able to find the solution for z using our linear techniques. And then if we've got our z, well, we can just set that equal to g of y and we're done. So was there a particular one of these four that you want to see, Victor? I'll let you pick A through D.
No, I was just thinking if this only applies for this form.
Well,
Clear that how to follow and solve the other ones when we have it in linear form.
yeah. So this one, this specific substitution only works in this specific form. But we will see later that there are other forms that we can do different substitutions and still be able to turn it into a form that we like. So why don't I run through, I'll do part C. I think C looks pretty good. So let me just real quick write it down. And then we'll head over to the whiteboard. All right, so this was C from that problem. So it was xy prime over y plus 2 natural logs of y equals 4x squared. Okay, so first thing I'm going to do is I'm going to divide by that x. I'm going to move that x out of the way because the form for the substitution we wanted needed to have just, I think it was called g prime times y prime plus something times g. So here's the substitution we're going to do. We're going to let z equal natural log of y. So then z prime is going to be y prime over y. So this turns into z prime plus 2 over x times z equals 4x. And this guy is now linear. It's linear for z, but that doesn't change how we find the solution. It's just instead of getting a y equals, it's going to be a z equals. All right, so let's think about the process. So recognize the form. First order, linear, non-homogeneous. So for the non-homogeneous, we have to start with solution to the homogeneous. So let's think about solving this guy. So we're going to get a z1. It's going to equal e to the negative integral of 2 over x. Well, that's going to be 2 natural log of x. So this is e to the minus 2 natural log of x, which is the same as 1 over x squared. Bring the minus 2 as an exponent from the rule of logs, then the e and the natural log cancel, so you get x to the minus 2. All right, so there's our z1. So then how do we get our z now that we've got this? What do we have to do?
The integral of 4x over 1 over x squared.
Okay, so now we're going to get that. We're getting our u, right? And use the integral of 4x over 1 over x squared. The 4x was the non-homogeneous piece. And then we divide by the 1 over x squared that we just found. So that's the integral of 4x cubed, which is x to the 4th plus c. And then we multiply that by the z1. So we get z is equal to 1 over x squared times x to the 4th plus c, or x squared plus c over x squared. All right, so we were able to solve that linear piece without too much trouble. But that's not the y, right? We actually need to know the y. Well, that's where we're going to use this. We know what z equals. Z is the natural log of y. So if we put that together with what's down here, we get the natural log of y is equal to x squared plus c over x squared, which means if we even want to get the actual y value, we can get this in explicit form. Y is going to equal e to the x squared plus c over x squared. Or actually, no. Forget that. We'll just leave it as it is. All right, so there is the solution then to our differential equation. And you could try, you could check it out. If you were to take its derivative, divide it by itself, multiply by x, take 2 times the natural log of this, which is going to be the stuff inside, you should end up with 4x squared. So this is just another end around. It's another way of manipulating it, turning it into a form that's useful. And we'll see this a lot. We'll talk about a specific kind of function, or sorry, kind of equation. And that specific kind of equation has a, do substitution. And that works because of the form. Anyway, so is that kind of better for this Does that kind of get at what you wanted, Victor?
Yeah.
Yeah. Okay. Cool.
So for the same set, part A,
Uh-huh.
would you use tangent or the secant squared
Let me pull it back up
for your
here.
y value?
Okay, so for this one, we're going to let z equal tangent of y.
Okay.
So then z prime is going to be secant squared times y prime. So this would look like z prime minus 3z equals -1. And then like in this guy, let's look at B. For B, I would actually let z equal e to the y squared. Because if I distribute that through, notice how we're going to have the 2x times e to the y squared. So then all the rest of this is going to be the derivative of z. And for part D, what would z equal?
1 plus y.
Not just 1 plus y, but 1 over 1 plus y.
Got it.
It might be that we actually need it to be negative 1 over 1 plus y. You would have to take the derivative and see if it exactly matches this. It might be off by a sign, or it might be off by some multiple. And that's okay, actually, because you can bring that back in when you do the substitution. So you get like a negative z prime, blah, blah, blah. Well, then just multiply by -1 to make it look proper for linear. Or if you got, let's say, 1/2 z prime, multiply everything by 2. Like if all you're off by is a scalar when you do that derivative, that's easy to take care of, because scalars can be dealt with in an equation rather easily. But yeah, this is just one of those where if you play the right trick, you can turn it into a form that's easier to do. All right, so any other questions regarding homework, that kind of stuff? Okay, well then I'm gonna assume that means so far so good. Right? We don't really have too many issues, and hopefully you're seeing that it really is just pattern recognition, right? It's looking at the form of the equation and thinking about, okay, well, what do I have to do to solve it, right? And what you have to do to solve it, well, that's just going to depend on what you're doing, right? What form it's got. All right, so with that, let's talk a little theory. Let's talk about when we know we've got solutions, what we need to be guaranteed solutions. If we have a solution, is there only one, blah, blah, blah. Because it turns out that it's actually really easy to determine, given a differential equation, at least the linear kind, or sorry, the first order kind, just looking at it and seeing where we're guaranteed solutions and whether or not we know it's going to be unique. So give me a second here, and I'm going to hop up to the whiteboard. All right, so we spent quite a bit of time now talking about how to solve first order differential equations. And we've seen really a couple of techniques. The first is if they're linear, super easy. We've also seen you can just do plain old integration if all you have is just the y prime. But we've also run into now separation of variables, which just means we have to be able to get all our y's on one side, all the x's or t's onto the other side, and then we can integrate. But the question still remains, will we always get a solution? Are there going to be solutions to these things? And the answer to that is no, not always. And I don't even mean like we ran into last time where we had to do some sort of integral of e to the x squared. Like, yeah, there's no nice function for that, but it's doable, we can make use of power series, like there's still going to be a solution. But there are flat out differential equations that don't have solutions. So what we really need to talk about is, when does that happen? So I've got a theorem for you. And this theorem has two parts. So the setup for them is all the same though, all right? So what we're gonna have is that we've got our differential equation, y prime. It's equal to some function of x and y. So basically, take your equation and solve it for y prime. You can always do that if it's first order. Okay? Well, what it's equal to, we're going to call it f of xy, or f of ty if we're in the t world. All right, and let's also have an initial condition such that y of x0 or x naught is equal to y naught. So we're going to be really generic here. Okay. All right, so here's an initial value problem. Well, here's the first part of the theorem. The first part of the theorem says, I'll say A, if f is continuous on an open rectangle that contains the point x naught, y naught, then there is at least one solution over an open subinterval. I'm just chuckling because, yeah, this is totally a math definition of interval that contains x naught. So I'm going to give you a minute to write this down, and then we'll talk about it.
What does that say after open rectangle that rotates?
Contains.
Contains.
So before I even give you part B, we're going to look at part A, and we're going to see what all this means. Because first of all, I bet you've never seen the phrase open rectangle. I know you've seen open interval, right? And I know that you've seen rectangle, but maybe not both together. Okay, so what do you guys remember about an open interval? Like, what did that mean if I give you an open interval?
Doesn't it go from negative infinity to positive infinity?
That is an open interval. That's an example of one.
We don't include the endpoints? Or
Okay, so it just means there are no endpoints to include. So you could have an open interval, say from 0 to 1, as long as it doesn't include 0 or 1. It meant that it was open. So an open interval just doesn't contain the endpoints. Or a better way to think about it is it's an interval that doesn't include the boundary. So an open rectangle is a rectangle that does not have its boundary. So if we were to draw on an axis here, so here's an x and y axis. So somewhere out here is going to be that point x naught, y naught. And an open rectangle about it would look like this. So here is an open rectangle that contains x naught, y naught. Okay. So what we're saying, at least for the setup here, is that if you can create a rectangle about your point, okay, so if you can create a rectangle about that point where the function is continuous on it, then you're guaranteed to have a solution. And that solution, when I say over an open subinterval that contains x naught, this rectangle, let's say, goes from A to B on the x-axis. So that would be the interval of x. When I talk about a subinterval, that just means that this is contained in the interval AB. So this doesn't mean that I'm guaranteed a solution over the entire rectangle. It just means I'm guaranteed in some interval, let's say here to here, columns C and D. Right? I know that there's going to be some subinterval that contains the point where I'm guaranteed my solution. All right, so that's what this first part is saying. You're going to look at your function, whatever y prime is equal to, and you're going to go, all right, is this continuous? If it's continuous everywhere, then you know that you're guaranteed a solution no matter what your point, no matter what your initial condition is. Notice that the initial condition is driving where we are. That's driving the point, which is driving the find a rectangle around it, which is then going to the solution that contains that point and everything. So it's the initial condition. But if we can look at an equation and see that this function is continuous everywhere, that's a good thing, because then you know for sure you're guaranteed a solution. All right, so that's the first part of this. Now, the second part has to deal with the f sub y. Okay, so now this one says that if f of xy and f sub y of xy are both continuous, on the same open interval or rectangle, sorry, then there is a unique solution. And then I'm just putting here the same over a subinterval, over an open subinterval that contains x naught. So like all the following is the same. All the trailing information is exactly the same. But go ahead and write that down. And then in a second here, we'll talk about this. Okay, so we got this continuous over an open rectangle, same exact idea. It's just now not only is the function continuous, but the partial with respect to y of that function is also continuous. And if that's the case, not only are we guaranteed a solution, I mean, we were guaranteed a solution from this part, right? The function being continuous from part A says that we know that it's going to be going to have a solution, at least one solution. But now the important word is that we're going to have a unique solution, meaning only one. There's one and only one solution to this. All right, so the name of this theorem, we call this the existence and uniqueness theorem, because that's what it tells us, right? The first part tells us that there exists, there is a solution. And the second part tells us that it's unique. So what we can do is, given a differential equation, we can actually start by just seeing, is there a solution? In this initial value problem, is there a solution? Is it even worth doing? Because if it's not, then why bother? Or if we know that it exists but isn't necessarily unique, that's good information. That means just because we find a solution doesn't mean that we're necessarily done. We might need to find more, right? So this is something that we should probably think about doing just about every time you're given differential equation, is just do the real quick, all right, is a solution going to exist to this initial value problem? And if it exists, is it going to be unique? It's because it's good to have that information going in. All right, so let me show you some examples. Let's actually just take some differential equations and we'll look and see where are we guaranteed solutions, where are those solutions guaranteed to be unique, what are the problem spots, and just kind of talk about them as we go.
I have a quick question.
Yeah.
For part A of
Yep.
this theorem, can there be more than one solution that's not unique?
Yep, that's what it means that, yeah, so when I say there's at least one, it can mean that there are 100.
Okay.
So you'll see, like, really what makes it so that it's unique is that the partial with respect to y is continuous. If this thing's not continuous, that's what opens the door for maybe more than one solution. And there definitely can be more than one. I'll show you an example. All right, any other questions on this before I erase it? Again, you can always go back, watch the video, kind of replay this. It's also in the book. All right, so let's look at this one. We'll start with a pretty easy differential equation. It's even one that you know how to solve. But let's look at y prime equals x over y. And I'm not going to give you an initial condition yet, but I will give you one in a little bit, because when we talked about this theorem, we needed to have the point that we were creating this open rectangle around, right? So we'll do that in a second, but let's just talk about this differential equation first. And let's look at both f of xy and the partial with respect to y of f. All right, so in this case, f of xy is equal to x over y. So it's always what y prime equals. So since y prime equals x over y, that's our function f. All right, so let's talk about this in terms of continuity. where is this continuous?
Everywhere plus or minus from the origin.
Okay, so the issue is with 0, and specifically y equals 0. So this is going to be continuous when y does not equal 0. So you get me away from 0, I know that this is continuous. So what this tells me is that there will be a solution. And when I say here a solution, that doesn't mean one, right? It just means there's going to be a solution. There might be more than one of them. There could be 2, there could be 3, there could be a million. But I know there's going to be a solution as long as y naught does not equal 0. So here are some axes. Choose your favorite point whose y coordinate isn't 0. Let's say it's right here. I'm going to be able to make a rectangle around that, where this function is always continuous. I just have to make sure I don't hit y equals 0. I don't hit the x-axis. So here would be an example of some such rectangle. All right, is that the only rectangle that can go around that and not cross the axis?
No.
No, there are an infinite number of them. I can make it as wide as I want, and I can make it as tall as I want, as long as I don't go anywhere above 0. And it doesn't matter where you set me off the axis. I mean, I could be really, really close to 0. Give me a y value of 0.0 with a million zeros and a 1. I'm still going to be able to go down a little bit and avoid the axis, right? So even like we barely have done anything mathematically, right? And in fact, I think the only thing we did mathematically, and it probably didn't seem like you set the bottom equal to 0. Ooh. But we're already starting to see that, yeah, this thing, we're going to get a solution almost always. The only time we're not guaranteed a solution is if our initial condition is such that y equals 0. Real quick before we go forward, because I just brought up something I want to remind you. Suppose I did give you an initial condition where y equals 0. Does that mean that we don't have a solution? No. It just means we're not guaranteed a solution. Right? There's a slight difference there. So all this theorem is telling us is if we're guaranteed a solution. It's not telling us, well, if that's not the case, then you don't have a solution. Right? All right, so it's kind of like if I say, hey, if you find a treasure chest in the forest, you're guaranteed to find money. Okay, does that mean you're not going to find money if you don't find a treasure chest? No. Someone might have dropped a $20 bill and you could still find money. I just can't guarantee that you're going to find it unless I know for sure, oh, you found one of the treasure chests, right? Anyway. All right, so that's what the function itself tells us. So let's look at f sub y. So f sub y, differentiating this with respect to y, is going to give us minus x over y squared. Okay, so same question, what's the continuity of this guy?
It's the same.
It's the same thing, right? So again, this is going to be continuous when y does not equal 0. All right, so what does that tell me? Well, remember up here where we said there will be a solution? Now we can say only one. So we have a stronger statement now. Now, not only do I know that there is a solution, I know it's the only one. And that's where we want to be. That's really where we want to be when we solve differential equations, is we want there to be just the one solution. Because if we have multiple solutions, then we have to decide, well, which one's appropriate to the thing that we're dealing with, and blah, 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 right? It's a lot better when there's there's one solution. So as long as our y doesn't equal 0 for our initial condition, you're guaranteed a solution. And not only are you guaranteed a solution, you're guaranteed that that's the one and only solution to the differential equation. All right, so that's kind of the process. That's what we're doing here with this theorem, is we're just checking for continuity so that we can see whether or not our solutions are unique. So let's actually run through this one with an initial condition. Let me give you an initial condition. Let's say that y of 5 is equal to -3. Since that -3 is not 0, I know that I am guaranteed a solution. And I'm guaranteed that that solution is the only one. So let's find it, because this is an easy enough one to solve. Let's actually find the solution. So this is separable. This is y times y prime equals x. Integrating both sides of that gives me y squared over 2 equals x squared over 2 plus c. I'm going to go ahead and multiply by the 2's just to get rid of the fractions. So we got y squared equals x squared plus c. Let's get that initial, or c, using our initial condition. So -3 squared plus, or sorry, equals 5 squared plus c. So 9 equals 25 plus c, or c equals -16. So we get y squared equals x squared minus 16. And I'm going to go ahead and get this into explicit form, because it's easy enough to solve for y. I'll just take a square root. So we have y equals the square root of x squared minus 16. But that's actually not correct. This one needs to be the negative square root. Negative square root. Well, let's start here. Do you guys see why it could be negative? Let's just go with the could be. We all good with why it could be? Right? When you take a square root, you get plus or minus. So why is it that it's actually the negative square root and not the positive square root?
Perhaps our initial condition, it equals -3.
Ah, that's not the perhaps. That's exactly right, Bradley. It's from the -3. Yep, good job, Ralph. So we see that this one, we have to get a y of -3 when we plug in 5. Well, if I plugged in 5 without the negative out front, I get the square root of 25 minus 16, square root of 9 is 3. No, that's not the right initial condition. I need the negative for it. All right, so when you're solving implicit, going from implicit to explicit, if you ever have one of those situations where you get a plus or minus, your initial condition should tell you which one. All right, well, so there you go. Check it out. Here is a solution. We found a solution, and it's unique. It's the only solution. There are no options in this case.
Is that a hyperbola?
Yeah, this actually is a hyperbola. If you were to take that and turn it into the form that you know for a hyperbola, let me do it up here. This would be x squared minus y squared equals 16. If you just shuffle some stuff around, which then when you divide by 16, so it's x squared over 16 minus y squared over 16 equals 1. So that's one where you're going to form your box. Happens to be a square. Draw on your diagonals. It's got the positive x, so it's going out in the positive direction. So the graph of this would look like this. But again, think about what we're doing. We're going to one of the points. The point is 5, -3. So we know that it needs to be going through, let's just say that that's this point out here. We need it to be a function. So we erase the positive side. So that's what this graph looks like. Y equals negative square root of x squared minus 16 looks like this. So there you go. Now, the other thing I want to point out is look at the domain on this. The domain on this says x is greater than or equal to 4, or x is less than or equal to -4. And for our specific one, because of that initial condition, we're actually in the greater than or equal to 4 business. So for our specific one, we would actually have to say, this is y equals square root of x squared minus 16, but then we put a comma, x greater than or equal to 4. So there's actually a lot to this. If you go to the explicit form, there's a lot that we have to watch out for, but it's all determined by that initial condition. The initial condition drove all of that to bring us to just that one little piece. So remember in the theorem where I said you're guaranteed a solution on a subinterval of the rectangle? This is why we have to put in that subinterval business. Because think about this, remember at the very beginning, we said we're good as long as y doesn't equal 0. So you could build any kind of open rectangle you want around that point. But suppose that we had built the open rectangle like this. This open rectangle contains our initial point, and it never crosses the y-axis, or sorry, the x-axis, so we're good with our function being continuous. But the thing is that our solution that we just found isn't over this entire interval from a to b. It doesn't work all the way from a to b, right? If this is a and this is b, we're going to be screwed here. We don't have a solution in that entirety. But if you look at what that theorem says we're guaranteed a solution over a subinterval that contains this point. Well, how about this for your subinterval? I'll go from, what was that, 4 to b. If I go on that interval, I'm guaranteed a solution. So that's why we have to put in that subinterval stuff, because it's possible that the rectangles we build go beyond where our function actually exists. But the fact that we can build that rectangle tells us that there will be a solution somewhere in that rectangle. I know, but you guys, after taking linear algebra, I think you guys totally understand how we have to be super precise and super deliberate with our definitions and super careful with how we say things. And this is yet another opportunity to CYA, right? Cover your ass. Mathematicians, we're all about that. We'll give you wonderful statements. This is always true when these conditions apply, right? This is always true, at least on an interval that contains this point. Okay, right. So, but hopefully you're still seeing the whole point of this is going in, we knew there was going to be a solution and we knew there was going to be only one solution. And we found it. There were definitely restrictions on where it is. But if all we're concerned about is there a solution? Oh yeah, no, we're guaranteed. As long as y wasn't equal to 0. All right, so questions on this example? I mean, maybe the question is, where the hell do we even start by thinking of questions? Okay, well, let's look at another one. And I'm going to do the same thing. I'm going to start you off with just the differential equation. Then I'll give you an initial condition and we'll talk about what the implications are. So here's another one that's pretty easy. It's y prime equals the 5th root of y. Also known as y to the 1/5. All right, so in this case, f of xy is the 5th root of y. So let's start with this function in terms of continuity. So where is this going to be continuous?
Everywhere, right?
Okay, so this one is continuous everywhere. Notice that there are no x's, so we don't have to worry about that. We do have to worry about the y's, but a 5th root of y, since it's an odd index, it's always good. You can even put negatives in, it's no problem whatsoever. All right, so what we know from this is that this is continuous everywhere. So what does our existence uniqueness theorem tell us now?
We're guaranteed at least one solution.
Yep. So there will be at least one solution. And then we just go put here for every IVP. So there's not an initial condition that you can give me that's going to cause a problem. I don't care. No matter what, I'll be able to find you a solution. So this one's really strong. We like this. This is huge. This guy, oh yeah, no, I got your answer. You give me an initial condition, I've got your answer. All right, so let's look at the partial with respect to y, and let's see what that tells us. So since this was the 5th root, or y to the 1/5, the derivative is going to be 1/5 y to the minus 4/5. So how about this one? Where is this continuous?
everywhere again.
Turns out not everywhere. I know why you were thinking that, Bradley. Watch out for this minus sign. That actually means we got y to the 4/5 in the denominator. So where's that a problem?
0.
Yeah. I'm going to put here continuous everywhere but y equals 0. So same kind of issue we ran into with the other example. All right, so what this tells us is that the solution is unique if y naught does not equal 0. So remember what I just said a second ago is that there isn't an initial value that's going to be a problem for finding a solution. And that's still true. I'm still going to be able to find a solution no matter what the initial value is. But what I don't know is that if that initial value is 0, I don't know that it's unique. I don't know that there's only the one answer. So if you give me a y that's not 0, yep, there's one solution and only one solution, and we're good to go. If that initial condition is y equals 0, well, I know there's a solution. I just don't know if it's unique. There might be more than one. So that's really the consequence of what this is right here, right? Is that there may be more than one. If y not equals 0. But there's a very important word in here. May. There may be more than one. I just don't know. Right? Just because I didn't prove it's unique doesn't mean that it isn't unique. I just don't know that it is. Okay, so there may actually be more than one if y not equals 0. All right, well, I'll tell you what, let's throw in an initial condition and let's solve it. And I bet you know what I'm going to make our initial condition equal. You know I'm going to let it equal 0, because otherwise it's stupid. Otherwise we know there's just one answer. Well, what if we don't know that? What if we go with an initial condition of y of 0 equals 0? Because now it's going to be impossible to draw a rectangle around that point so that this function is continuous everywhere in that rectangle. Because that rectangle contains a point that's already a problem. Right? Well, let's see if we can go ahead and solve it though. So this is another one we're going to do by separation. If I move that y to the 1/5 down below, this is y prime over y to the 1/5 equals 1. So that's y to the minus 1/5 times y prime equals 1. All right, so integrate both sides. Add 1 to the exponent, divide by that value, we get 5/4 y to the 4/5 equals x plus c. Let's go ahead and find our c while we're here. Putting in our initial condition, we let y equal 0. And x equals 0. That tells us C equals 0. So I'm just going to rewrite this as y to the 4/5 equals 4/5 x, divide by the 5/4. And then I'm going to go ahead and solve it for y. And so here is a solution to that differential equation. If you take its derivative, and then you set that equal to the 5th root of this, you get exactly the same thing. And it passes through the point 0, 0. You can see that pretty easily. Okay, so we were guaranteed a solution because the function itself was continuous everywhere. So we were guaranteed a solution. But this is not the only one. That's not the only solution to this initial value problem. You ready for another? Really easy. How about y equals 0? So think of that, that's just the horizontal line, y equals 0. Does it go through this point? Yeah, goes through the origin. Does it satisfy the differential equation? Sure. The derivative of 0 is 0. The 5th root of 0 is 0. These are two very different functions. Very different functions. And yet they're both solutions to that differential equation. Okay, so the moral of the story with this one is that you can still be guaranteed solutions, but not have them necessarily be unique. And even though there was a super easy way to solve it, I mean, like when we solved this, everything was perfectly fine. We did all the steps properly. Right? It's just, it wasn't the only one. Y0 also works. So here's the question, is there another one? Is there a third function that's different than these two that still satisfies that initial value problem?
Y equals X.
All right. Does y equal x? It definitely goes through the point. If we put it in the derivative, though, derivative of y equals x is just 1. And this would be the 5th root of x. 5th root of x doesn't equal 1. So that one's not a solution. But I asked that question not actually expecting an answer because the answer is, I don't know. Could there be a third one? Sure. There could also be a 4th and a 5th, and there could be 100 different ones. We don't know at this point. The best we can say is that we know there's going to be a solution that goes through the origin. Could there be more than one? Yeah, we found more than one. Are there only 2? I don't know. But I can also tell you that if I were to change this, instead of having y of 0 equaling 0, if I had made it say y of 0 equals 1, you know what I can tell you now? There is a solution, and there's only one solution. So if we had gone through that, like, and this is where we could have done this exact same process, plug in the 0 for x, the 1 for y, get our c at this point. That one is the one and only solution to that initial value problem. Okay, so take this theorem for what it is. It's very useful in telling us if there are solutions. And it's also very useful if it tells us that it's a unique solution. But if we run into this situation where we're not guaranteed it's unique, it doesn't tell us anything. It might be unique, it might not be. If it's not unique, how many are there? I literally do not know. It depends. It depends on what the function is and all that. All right, well, these theorems I know kind of suck because we prefer having those theorems that are all or nothing. I mean, no, this theorem is great in the cases where like both f is continuous and f sub y is continuous everywhere. We love those because then it's like, yep, one solution, no matter where we are, everything's good done. It's those other places that we don't like it because these theorems tell us absolutely nothing. They don't tell us the opposite, right? Like if we had a place where it wasn't continuous, that doesn't mean there isn't a solution. It just means we're not guaranteed it. Fy is not continuous, doesn't mean it's not unique. It just means we don't know that it's unique.
I can't remember, but if a function is a function still considered continuous even if it approaches an asymptote?
It will be discontinuous at the asymptote.
Okay.
If it's a vertical asymptote.
Mm-hmm.
If it's a horizontal asymptote, those don't affect continuity whatsoever.
Okay.
But a vertical asymptote is a discontinuity at the asymptote.
Got it.
Yep. Yeah, so if this had been, like over x or something like that, then there's a problem at x equals 0, which would be probably an asymptote issue. Yep. All right. So here's another example. It shows what it should. Now, what I'd like to do is go back to linear first order. I want to go back to linear first order so that we can talk about what are the conditions that we need for linear first order to guarantee solutions and guarantee unique solutions. Just because those were special, right? We got a great process for them. They all have the same form. Let's take a look at those and see what this theorem has to say about linear first order. All right, so let's go back to that. So a generic linear first order was the one that looked like y prime plus p of x times y equals g of x. So we're going to be nice and generic. We'll even allow for non-homogeneous. Well, let's just think about what this has to look like in order for us to know existence and uniqueness. Excuse me. All right, so first thing we're going to do is we're going to write this as y prime equals. So I have to move that piece with the p and y over. So we get y prime equals g of y minus, or say g of x minus p of x times y. And we did that because this, all that's on the right-hand side, is now our f of xy. Okay, so let's think about this in terms of continuity. Well, let's answer discontinuity. So where are we going to have problems with continuity with this f of xy?
I mean, doesn't that really just depend?
Depend on what?
what those functions that make up f of x, y are?
Yeah, totally. It depends on G and P, right?
Yeah.
And so here's what we know. We know that this is going to be continuous if G of X and P of X are continuous. It has no dependence on Y whatsoever. So in this regard, given an initial condition, the Y value doesn't matter. It only matters the X value. And that only matters in as much as it doesn't affect the two functions G and P. Okay, so if both of those are continuous, then we know we're going to get a solution. We just don't know if it's unique or not. All right, so then let's look at Fy. If I take the partial of this with respect to y, G of X goes away. The minus P of X is a constant multiple. And of course, the derivative of y is 1. So we get f of y is equal to minus P of X. Well, this is kind of the same deal, right? This is continuous if P of X is continuous. All right, so let's think about what this means in terms of a blanket statement we can make. All right, so here's the best I can say. For linear first order, I can say if G of X and P of X are continuous, I'm going to put here are both continuous, then there will be a unique solution. So given your function, or given your differential equation, if you look at those two functions, P and G, if they are both continuous, you're guaranteed a unique solution. So notice how the first part said we were guaranteed a solution. But I know that it's guaranteed to be unique because the condition for unique was the same as one of the two conditions for existence. So linear first order are actually kind of nice. Because if you're guaranteed a solution, you know it's unique. And the only issues you're ever going to have are with the P and the G. What do those functions look like? Are they going to be problems? Are they not? So homogeneous are even better. Because if we're talking about homogeneous first order, so let's add that on here. So we'll go homogeneous linear first order. That, of course, changes this just to y prime plus P of X times y equals 0. The G is now 0. 0 is always continuous, so G is always continuous. So all of this comes down to just P of X. So the statement we can make for these is, excuse me, if P of X is continuous, there is a unique solution. There's one and only one solution. And we find it using our process. E to the negative integral of p of x. And I get the c from whatever our initial value is. All right, so that's what this new theorem tells us about older stuff. We can now go back and look at any one of these that you did. You're going to be able to see that you're guaranteed a solution and a unique solution on any interval where our functions were continuous. So think back to one. We just did this. It was one of the homework questions that Victor asked about that involved that substitution thing. This may not be exactly what it was, but it was close. It was like z prime plus 2x, 2 over x times z equals, let's just say it was 2x. It was some, no, 4x. It was 4x. All right, so you remember this guy? So instead of z's, think of it as y's. But let's look at this from the context of solution. All right, so g of x, 4x, continuous everywhere. P of x, 2 over x, that's continuous everywhere but 0. Right? So we know that we're going to be guaranteed a unique solution when x does not equal 0. Now, I don't remember if there was an initial condition to that. I think there was, but I don't remember what it was. But I want you to go back and look at what the solution was. We found that we got a solution of, it was what, natural log of y. All right, let's just go to the z. So z was equal to x squared plus c over x squared, I think is what it was. And I just want you to notice this, that we knew that we were good as long as x doesn't equal 0. And in fact, you even see that in our solution, right? If x doesn't equal 0, no problem. Our solution is going to be good as long as we're on one side or the other of 0, which totally matches what we saw here from the existence uniqueness there. So it all goes together. It totally all goes together, and hopefully you can start seeing that. But yeah, there you go. There's existence and uniqueness. All right, so questions on the linear first order? Is it kind of making sense how that fits into the rest of the big picture with this theorem?
As far as the non-homogeneous differences,
Yeah.
Does the process remain the same as far as solving? That doesn't change at all, right?
No, it's still going to be the same. And in fact, you're going to see the same issues, right? Like, you know how this says we have to have g of x equaling or being continuous. Think about where g of x comes in the process. It comes in when we try to find our u, and we're trying to integrate that divided by p of x. So we're trying to integrate a potentially discontinuous function, and that can be a problem, even if it's, you know, even if the integration itself happens, the end result will still have that limitation in it. Like a good example, think about 1 over x. It's not defined at 0. Its integral we can do, natural log of x, that doesn't let us go past 0, right? So the process doesn't change. All of the issues that come up are going to be taken care of in the functions that are the antiderivatives or whatever else we find along the way. That's a good question. Any other questions on this? All right, well, I just looked at the time and we only have 10 more minutes. I think we're probably good at this point. So I'm not going to show you another example. I think you know what you need to do and what you're looking for. Just make sure that you write it in the right form. And look at those derivatives, look at the function and then the partial. And it tells you an awful lot. So in the homework, it's going to ask you things like, where are you guaranteed a solution? Where are you guaranteed a unique solution? Things like that. It's not going to necessarily ask you to solve them. A lot of them is just tell us where it actually, where existence and uniqueness is guaranteed. All right. Okay, so I'm just trying to think of things I need to remind you about. Homeworks. First set of homeworks are due tonight at midnight. I think that's what 1, 2, 1, 3, and 2, 1. I know some of you have already turned them in. Thank you for that. Already graded a few of them. But make sure you get those submitted to me by midnight tonight. Other than that, I'm going to wish you all a wonderful couple of days. And on Wednesday, we'll just keep plugging along. All right. So have an awesome couple of days. See you Wednesday.